Let's talk now about polyprotic acids. These are acids that have more than one acidic proton. For example, sulfuric acid, H2SO4, has two H's, both of which can act as acids. And we're going to see that, in general, most polyprotic acids follow one of two trends that we'll see, depending on the differences in their Ka values. We'll see if there's a small difference between their Kas, we do have to pay attention to all the protons involved. However, if the Kas are significantly different, we can kind of just ignore the second or third one, depending. But let's take a look at an example here. Let's look at carbonic acid. Carbonic acid is H2CO3. It has two acidic protons. And I have the data here. When H2CO3 dissociates, remember we always do this with one proton at a time. So we end up making bicarbonate and H+, and that bicarbonate can dissociate some more, again. And we have two different Kas for these processes. We're going to see that the first one we call Ka1, and the second one we call Ka2. The first proton you remove is always easier. So the first Ka is always lower than the second one. And so we see here that the first Ka is about 10 to the negative 7. Ka for the second one is about 10 to the negative 11. This is a pretty big difference. The rule of thumb is about 10 to the third. So this is a 10 to the fourth difference. If your acids have Kas, or if your acid is singular, and its conjugate base, which is also acidic, has a Ka difference of about 10 to the third or more, we can ignore the second one, or whichever one happens to be the difference of 10 to the third. So sometimes with like phosphoric acid, for example, we might be comparing Ka2 and Ka3, because that one has 3 protons. But in this case, we see that the difference between carbonic acid and bicarbonate's Ka values is about 10 to the negative 4. And we're going to see through an example that the amount of acid coming off from the second dissociation is negligible compared to the first. So let's go ahead and say we have the pH of 1 molar H2CO3. Let's see if we can calculate that. With the first one, I'm going to just copy paste here. We have our Ka and we have our equation. We're going to start with 0.1 molar. We're going to have nothing here for each of these. This is an ice table. Plus x, 0.1 minus x, x. So we get x squared over 0.1 minus x equals 4.3 times 10 to the negative 7. If we make our assumption, we say x squared is, the minus x is negligible. Let's see what x is equal to here. So we're looking at 4.3 times 10 to the negative 7 times 0.1, right? The square root of that. We get 2.07 times 10 to the negative 4, so that's definitely less than 5%, so our assumption is okay. So remember, we make that approximation. With that in mind, we can see for the first equilibrium, we can see our concentration of H2CO3. Actually, we don't care about that. Let's look at H+. H+ is 2.07 times 10 to the negative 4 molar. And the bicarbonate, since this is the time we're going to actually need to know this number, would be the same value. It's 2.07 times 10 to the negative 4, because they're both x here on our ice table. All right, so that aside, now let's do the second dissociation. Let's take a look at that second one and see what we can do here. So now that we have this, we have our bicarbonate ion dissociating into H plus and CO3 2 minus. This time we do have starting values. We're going to have 0 of the carbonate. Of course, that's going to make our Q equal to 0. And since Q is equal to 0, we're going to, again, proceed in the dissociation. So here's our ice, minus x plus x plus x, 2.07 times 10 to the negative 4 minus x, 2.07 times 10 to the negative 4 plus x, and x. All right, and so this one's going to be slightly more complicated. We get 2.07 times 10 to the negative 4 plus x times x over 2.07 times 10 to the negative 4 minus x equals our Ka, which is 4.8 times 10 to the negative 11. If we assume that the plus x and minus x are negligible, that means we can actually just get rid of these, assuming that that x value is less than 5%. And in doing so, x is 4.8 times 10 to the negative 11, which, as we can see, is definitely less than 5% of our 0.1 molar to start with. So, but we see here 10 to the negative 11 for this H plus concentration. I mean, technically speaking, we'll need to go ahead and add this number to our original acid concentration. 10 to the negative 11 added to something 10 to the negative 4 means nothing. It's still 2.07 times 10 to the negative 4. Through sig figs, this number just goes away. So we see our concentration of H plus doesn't change, really. The amount added by the bicarbonate ion is so small that it's not worth calculating. We see because that Ka2 is so much lower than Ka1, we can ignore it. So the pH is really just the H plus from the first dissociation. We don't need the second dissociation because it's so small, it just goes away with sig figs. So we're going to do our negative log of 2.07 times 10 to the negative 4, negative log 2.07 EE negative 4, and we get 3.68. We have 3 sig figs we need, so here's a 4. Okay, there we go. That's our pH. And so again, we see that this 4.8 times 10 to the negative 11 didn't do anything for us. It's too small to be figured in here. And so in fact, since it's negative 11, the associated water is pretty close to that, right? 10 to the negative 14. So, all right, so the point here that I will write in purple, if Ka1 is bigger than Ka2 times 10 to the third power, we can ignore Ka2 and so on. And again, this relationship still holds for something like Ka2 versus Ka3, for something that's triprotic, meaning there's 3 acidic protons. So you can basically just ignore the next one. So say if Ka1 and Ka2 for phosphoric acid are pretty similar, but Ka3 is bigger than a difference of 10 to the third, then we could ignore Ka3. We just deal with Ka1 and Ka2. Otherwise, you need to do the ice table for both. You need to do the ice table for both, just like we did in this example. And you have to carry over your values. So notice that our initial concentrations of bicarbonate and H plus were calculated from the first dissociation. The first time our carbonic acid lost a proton, we made HCO3 minus and H plus. So we have some initial concentrations for our second ice table. So just keep that in mind. Generally speaking, most acids you can kind of ignore the second Ka, at least for now. As we get into our next chapter in a while, we'll see that when we're reacting these acids, we have to deal with Ka2 again. But for right now, if you're just looking at pH, we can generally ignore Ka2 if it is a difference of 10 to the third or more between the two.